thank you for being here. It's an honor for me to be here with you and to share some of our latest research on climate technologies. I'm Bernd Heid. I'm a senior partner at McKinsey here in our New York office. I lead our platform for climate technologies globally, and in that respect have worked with industry companies and also with startups on the scaling of climate technologies, and I want to share with you some of that data today. So first of all, what is climate technology? When we speak of climate technologies, we think of 12 different technologies. And altogether, they more or less account for 90% of the decarbonization potential. So we know these technologies. 90% of the technologies are known to us. There's a whole bucket about the green electrons when you think of energy storage, batteries, renewables, heat pumps. But we also think of molecules like hydrogen or any of its derivatives, methanol, ammonia, or e-fuels in the broader context. We need carbon management. That's carbon capture and storage technologies, or think of nature-based solutions, and also circular technologies and resource-based technologies. Altogether, that accounts for 50 gigatons of CO2 abatement, and that's more or less the 90% chunk of what we need to get to net zero. So the good news is we know these technologies. It's not that we have to invent new technologies, but the problem is that they are not scaled yet. So if you look at this chart, you basically see where do they stand in terms of commercialization and scaling. And you see on the far right that only 10% of these technologies are globally deployed. And when we think of globally deployed, we mean that this is a business case that it's in the money. So you have that for certain parts of solar, you have that for certain parts of wind, but by and large, if you look at the 90% of the technologies, they are not there yet. So they are not in the money, and that's the obstacle. We need to scale these technologies to make a profitable business out of it. I would love to put our emphasis on the second bucket, the 45% that are in commercialization. That is where the scale up happens. On the far left, that's tech, that's deep tech in university, in labs, and so on. But like really where we can make a difference is on the 45%, think of hydrogen, think of battery electric vehicles and so on, where you more or less need the scaling to bring these technologies into the money. So this can be done. On this chart, you see more or less both the track record and then also the extrapolation what could be or is needed to scale these technologies. And you see the left part of here some selected technologies where we have seen scaling of somewhere between 20 to 60% annually in order to deploy them. And if you look forward, it would require in a similar trajectory forward-looking to make these technologies viable. Some of them still have a very steep curve ahead if we want to get to net zero. But even if we don't achieve net zero, that is a trajectory that we can certainly follow for various different technologies. So let's look at them in difference. What is the difference between a technology that scales and what doesn't? So therefore, I want to highlight here just a few. And we have like more or less two different types, yeah? So the one is where we always see delay, yeah? You see the curves show more or less projections from the past and then projections updated. And you see that for some technologies, we always push out the projection, almost like a hockey stick that keeps on moving. And nuclear fusion has been a technology where people say that's 20 years out. But it's always 20 years out, regardless when you ask it. And hydrogen, which is one of my favorite technologies, is also technologies where we have seen ups and downs a couple of times. At least I have witnessed 3 of these cycles. But on the other hand, we also have technologies where we consistently have forecasted that wrong. And that is, for example, solar. If you look at the solar curves from 2006, and then look at what solar really deployed and happen. The same for onshore wind. So apparently there's something to it, that some technologies get pushed out, others don't. What is that? And that's in essence, it's a scaling of the technology. It's a manufacturing scale up. If you deploy a technology at larger scale, that brings down the cost and that makes these business cases viable. So, there you go. So this is a chart where we see whether there's a business case or not. So again, you see the different technologies. Blue dot always means that is basically today, 2023, and the orange dot is the projection forward-looking. So the good news is that we see a trajectory of like minus $100 per ton of CO2 that we have in a decade. Yeah, 1 decade. $100 equivalent per ton of CO2, and you see that they come in the money. The green area is a zero line, so the y-axis more or less shows you what's the required US dollar abatement cost per ton of CO2 and whether it's in the money or not. So everything that's below the zero line means a negative money. Negative number, that means the technology is in the money. Every number that's above it means you have to offset it with like 100, 200, 300 US dollar. So what you see, that's as of today, including the projection for 2030. And what you clearly see is that most of the technologies are not yet in the money. And even if you take the projection up until 2030, you see that only 5 or 6 of the technologies, namely the ones that I mentioned earlier, solar, wind, heat pumps, are more or less economically viable. So what that implies is basically that we need some sort of carrying that burden of the economic deficit. That could be a carbon tax, it can be incentives, yeah? But there needs to be something that more or less helps these technologies to get into the money. And here's the same chart. We just lifted the curve up to $100 per ton of CO2, which is a fairly reasonable carbon price. But you see with that carbon pricing that more or less 15 out of the 35 technologies get into the money immediately. And it also means if we translate that into CO2 abatement, you see that 50% of the CO2 abatement is in the money. But it requires more or less a carbon price. And if you go back, that's a chart without the carbon price, and that's a chart with the carbon price. And you easily see the difference, what a carbon price can make. So let's think of a couple of obstacles. How do we get in the money? And this is a chart that gives a correlation between the technologies and the cost down potential. And it shows very, very clearly that with a scaling of the technology, regardless whether it's an early innovation or whether it's already globally deployed, you bring these technologies in the money. So it is a cost down as a function of the scale of the technology. And we normalized it to abatement potential. So the x-axis means how much CO2 is avoided, yeah? Whether it's 1 kiloton, 10 kilotons, 100 kilotons, and then the cost of these technologies. And this is empirical data. This is not a projection. This is like real data. And the good thing is, it doesn't matter in what part of the technology stage you're in, whether that's a lab scale technology or whether that is something like solar that is already globally deployed. We called it Moore's Law of climate tech. I didn't dare and go so far to call it Heid's Law of climate tech. But I found it quite stunning to say 100x in deployment minus 70%. So easy, yeah? It doesn't matter which technology, what stage of the innovation is, 100x in deployment minus 70% on on the cost reduction. And that more or less gives hope because it shows the correlation between if we are able to scale it. It's not about new invention. A lot of that is manufacturing engineering that helps to bring it down. If we build battery factories at scale, that brings down the cost. If we build electrolyzers at scale, you don't do batch-wise process, but you bring down the cost. So let me show one more obstacle that we see in this market as we scale. And this is one of my favorite charts. I think it should go in an art gallery. What you see on this chart is the correlation of energy production of the future and energy consumption. So the way to read it is you have the dark green or dark blue areas. Those are the future energy sources. And it's very natural. They correlate mostly to where do we find renewable power, where do we find cheap natural gas and have the opportunity to do carbon capture process. And then you have the orange circles, which is the industrial GDP, excluding energy. So what it means is basically we say, where do we use energy in the future? That correlates to the global north. And where do we produce energy? And a lot of these energy production hubs are new hubs. Think of Australia, India comes in. Of course, Middle East is gifted with both fossil energy, but also renewable energy. But then if you do the math, and we have done that in a model where we did like 1.5 million permutations of like sources of energy and consumption of energy. And this is like a flow model where you say like we will need energy to travel the world. And people say like we can do that with electrons. So fossil energy is easy to transport around with a ship or pipeline. So we got used to it. But we haven't thought how do we transport renewable energy in the future. And electrons alone will not do the trick. You cannot export sunshine out of Australia in the form of an electron to, let's say, Europe or North America. So here is where the molecules come in, and that's also where we have this systemic angle, that it's not like one technology can solve it, but we need multiple technologies at once. And then you also understand why it is okay to convert electrons in a molecule, even if you lose energy. And you have heard the argument, why do we waste energy by converting electrons into molecules? So like if you can use the electrons straight without conversion, go for it. It's always the cheapest and best opportunity. But in absence of a proximity between production and consumption, you're better off if you convert that into molecules because you can ship molecules around. So, but there are a couple of obstacles, but I would love to highlight the opportunity that's in there. So as of today, this market of climate technology is about a little shy of $1 trillion US, and more or less doubles every decade. So we speak here of a $4 trillion opportunity in equipment value chain that is here at stake. And just to give you a correlation, that represents 3% of the global GDP. That's the entire global auto industry today, what climate technology can contribute. And that's why I'm also so enthusiastic about climate technology, because it's something that helps the entire world. It's like the Western industrialized countries, the US, Europe, Japan, Korea, China, they benefit from deploying that technology because it creates jobs, it creates innovation. So it's something that we benefit from. But at the same time, the global South also benefits because we have the opportunity to produce energy in these places. So technically, this is an enabler that we improve the wealth of the entire world, not only in the industrialized North. So, but unfortunately, there are obstacles. Here is one correlation that you see. They come in pairs. There's never a technology alone. So the chart, as you see it, has overlaps between the various different bubbles. The bubbles represent the size of the CO2 abatement. And you see basically on this chart how they interlink. And let's pick hydrogen with 5 gigatons in here. You see it's fully overlapping. It's overlapping on the one side with renewables, because for every molecule of hydrogen you produce, you first need the electrons to go into the electrolyzer. Or vice versa, if you take blue hydrogen or hydrogen that is made from natural gas with a steam methane reformer, and you capture the CO2 and store it underground, you first need the carbon capture technology. So that's why you see the overlap here. And I could go on, think of e-kerosene in aviation fuel. For every molecule of synthetic kerosene or methanol or ammonia that you power marine ships with, you first need a hydrogen molecule as a precursor. Without that molecule, you will not be able to do these longer chained hydrocarbons. So therefore, you see that climate technology, there is not like one silver bullet and that saves the world, but it's literally the combination of these technology. 60% of the full potential is more or less overlapping. That's more than half. So therefore, when people say that they found the one technology that will solve it, I would always get skeptical, because we have so many uncertainties in the deployment of these technologies, and I think we need to be technology open in order to find the abatement. So let's close and see what is needed. So number one, I think wait and see is not an option, and we have seen ups and downs just in the last 18 months. Think of what happened there. We had IRA with a great impulse on further deployment. At the same time, we have seen cost increases. Hydrogen projects became more expensive than they became cheaper. Renewable energy became more expensive than cheaper. And a lot of that has to do that we put again a price to financing these. So we have higher interest rates. These interest rates go straight into the projects. So therefore, by and large, you could say, then why don't we wait? You have shown us the curves, and they all show in the early to mid-30s, that's where the real momentum happens. Why don't we just wait until then? But the costs do not come down. There's a learning curve. If you want to deploy a 2 gigawatt hydrogen project, you'd better start with 200 megawatt. Take the learning, do the next iteration, scale and deploy, and you have to do that in cycles. So therefore, wait and see is not the right answer for climate tech, and we need to match more or less the offtake and the cost down. The second thing is, I call it climate change is a market failure. What do I mean with that? It's when you have seen the charts earlier, there is a price to decarbonization. Decarbonization doesn't come for free, and that's in essence the $100 carbon price that I alluded to earlier. If we want to decarbonize, someone has to pick up a bill for it, and that's either us as consumer, it needs to be public money, or it needs to be companies that take a risk now at no positive business case in order to enter business. But decarbonization has a cost attached to it, so therefore it doesn't come for free. And that's how we need to find matching pairs of technology plus the offtake, the end user demand, plus governments that help in de-risking that. And the last one is the role of green capital. How can we get green financing deployed? Yeah, and we hear a lot about green finance, but it's not deployed at scale because the internal rates of return that private capital requires doesn't match these business cases. So we need to be smarter in connecting public-private partnerships, public money with private money, venture and and other forms of financing that needs to work together. It will not work to just wait until we have the business cases that deliver the returns that we are expected from normal business. Let me pause here. I thank you very much, and I hope I could share a couple of insights.